Okay, so
Okay, can you see my slide? Can you see
yes,
my screen?
Professor. Yes,
Yeah.
Professor. We can see it. Before you start, should I give a brief introduction about the ScholarPath so that when we post it to YouTube or other platforms, everyone can know what is going on and what this talk is centered around?
Sounds good.
Okay, so good afternoon, and we are from ScholarPath today, and I am Aryan Chaudhary, the president of ScholarPath, an independent student-led research and mentorship initiative built on a simple premise that direct access to the world's leading scientists shouldn't be reserved for students who already have the networks to reach them. Today's guest works at the frontier of gravitational physics. Professor Claudia de Rham is a professor of theoretical physics at Imperial College London, where she directs the Abdus Salam Centre for Theoretical Physics. Her research sits at the interface of gravity, particle physics, and cosmology, and she is one of the architects of the modern theory of massive gravity. Professor De Ram is a Simons investigator, a recipient of the Blavatnik Award for Young Scientists, and elected member of the American Academy of Arts and Sciences, and the author of The Beauty of Falling, A Life in Pursuit of Gravity. For the next 40 minutes or so, we'll move through a research program, the institutional structures like the Abdus Salam Centre that connect global physics to students in places like Nepal or other underprivileged countries, and a view on what it takes for young researchers to contribute meaningfully to an open problem. Professor, thank you very much for being here, and the floor is yours now.
Thank you very much. Thank you, Aaron. And it's really, really a nice, very strong pleasure to be here. Thank you for the very warm introduction. And it's good to see you. There are a few people there that I can see in person, and I'm sorry I can't see everybody. So, yes, I'm Claudia de Rham. I'm, in fact, the director of the Imperial Abdus Salam Centre for Theoretical Physics. And I'm really, really happy to be here because the Abdus Salam Centre for Theoretical Physics at Imperial was very much founded within the premises of three major vision. And I think being here with you today, that really embodies and captures those three very important mission of the center. The first one is excellent in scientific research and pushing the frontiers of knowledge. And so I'll show you a little bit of some of the things we do in fundamental theoretical physics related to my work. But also the two other missions of the center is very much following also on Salam's other legacy in using theoretical physics, using science as a unifying tool, as a unifying force, really, across nations. So I'm really very happy to discuss with you and engaging with you in a way that we can really collaborate together in the future. And also as a unifying force, not only across nation, but also across society. And so using science as a way to engage and transmit, inherit the thought process throughout society, because I think it's really very exciting about how we think about some of the fundamental laws of nature. And let me just say very quickly that, in fact, no matter what a problem we may have for tomorrow, I do strongly believe that nature has had the strongest level of the strongest level of impact in finding solutions for all of the problems that we can think of. So for us, understanding the fundamental laws of nature, understanding how nature has been able to find solutions from some of the most fundamental problems is our way as well for us as a society to be able to find and formulate solutions to some of the problems that exist today and that will exist tomorrow. Okay, so enough about this little spiel. I'm a cosmologist. Let me give you a little peek into the life of a cosmologist. And before I go there, let me just tell you that cosmology is a little bit different than cosmetology. I would like to say that cosmology is the study of the universe. It's really understanding the beauty of the universe as a whole, whereas cosmetology is the universe of beauty. So I'm really much more interested in cosmology because it's really the underlying of everything that we know of from the fundamental laws of nature and how that applies to the largest possible scales in our environment. But the universe itself is governed by one of the most fundamental, one of the most powerful phenomenon that exist, which is that of gravity. And so understanding the universe, its origin, its evolution, its composition, really requires having a very deep understanding of that phenomenon, understanding of gravity. So I'll spend, in fact, quite a lot of time discussing about gravity. And what I'd like you to do is try to understand, first of all, what is gravity on a more human level? How do you feel gravity? What is a feeling of gravity? And you may wonder whether that question makes sense at all. What does it mean to feel gravity? We could ask ourselves, what does it mean to feel light? And that will have a better perspective, what it means to feel light of electromagnetism. In fact, we interact with it in a way that our body is able to understand that phenomenon. But for the point of view of gravity, in fact, in our everyday life, we may have the impression we understand what this phenomenon is, we understand that we are attracted to the earth, but the feeling of gravity itself, the way we think of it, is actually not about gravity per se. Typically, when we think about gravity, we have a negative impression of it, and what we think of gravity is more the end of a fall, is the end of the gravitational process, where, for instance, we're feeling the bottom of our chair on us, we're feeling the ground on our feet, but that's not really gravity. This is more related to Pauli exclusion principle, which prevents different electrons, for instance, or different states to be at the same place at the same time, and so prevents us from falling through the earth or falling through the chair. Was to really appreciate and understand gravity, we need to extract ourselves from all of those distractions. And that on Earth is quite difficult because we have the ground, we have the furniture in your room, we have the air in that we breathe. And so to really feel gravity more plainly, we should extract ourselves from all of those distractions. And to think of a feeling of gravity, you can rather imagine yourself in outer space where you're free from those distractions. So let's imagine yourself in outer space orbiting the Earth. And so the Earth will still be there. You're still experiencing gravity, but in that occasion, you're experiencing gravity so freely, you're embracing yourself to it so fully that you don't feel anything at all. And you don't think anything at all because every single particle in every single atom, in every single molecule, in every single cell of your body, and the air in your spacesuit and your spacesuit itself is experiencing gravity in exactly the same way. And there's something very fundamental, very non-trivial, and very profound about gravity, which is related to a kind of symmetry, which we call the universality of gravity, or the equivalence principle, that tells us that gravity affects everything and everyone all the time throughout the universe in exactly the same way. And so gravity is not pushing our cells apart, and there's no way for different cells to experience gravity in a different way so that we can actually feel gravity with our body. This notion of equivalence principle is something that you probably have heard of and was already postulated by Galileo so many centuries ago. And I just want to illustrate this, not here on Earth because it is hard to do it here on Earth, although it's of course been done. But it may be easier to think of it if you are on the moon, not because gravity is any different on the moon, it's not, but simply because there's no atmosphere on the moon. So you're not distracted by the different way things fall through the air. You're just experiencing gravity more plainly. So this one of this best illustration, it's just an illustration more than a test itself, but best illustration of this phenomenon of equivalence principle of gravity or universality is captured by astronaut David Scott in 1971 during the Apollo 15 mission on the moon. And the quality of the picture here is not great, but when I press play, hopefully it'll be a little bit better. And you'll see that on his right hand, there's a hammer. You can't quite see it here right now, but you will see later. And on his left hand, there's a feather. And when he lets them go, they will fall at the same rate under the gravitational attraction because there's no atmosphere, so they're not bogged down by different friction of the air. And so that illustrates this equivalence principle. So let me show that to you. The sound doesn't work, I'm sorry. Let me show it again. So you have a hammer here and a feather here. And it's a shame the sound is not working because hopefully you can see in that video that indeed they are experiencing gravity in the same way, the hammer and the feather, independently of what kind of objects they are. But something else, which I think is even more cool when you hear the sound, is to realize how excited that astronaut is to, in fact, testing gravity. And I think if there's anything at all that I'd like you to take away from this talk, is that we humans are incredible explorers. You can imagine yourself, you are one of the first humans to set foot on the moon. And what he's the most excited about is, in fact, just understanding the laws of gravity, the laws of nature. And that in itself, I think, is a tremendously powerful lesson. So now let's go back to gravity. We understand now for 4 centuries that there is this equivalence principle and that gravity is affecting everything and everyone in exactly the same way. And it is very much this universality that pushed Einstein to understanding a century ago that if gravity is so universal, this universality cannot just be an accident, and the information about gravity itself cannot be encoded in the objects themselves. The information about gravity has to be encoded in something deeper than all of us, something immaterial in some sense. And so this is really what pushed Einstein to understanding that gravity is encoded, in fact, in the very fabric of space and time. We now understand, thanks to Einstein's theory of general relativity, that masses like the Earth, for instance, or anything at all, but it doesn't even need to be a mass. It can just be anything that exists, that has energy, that has pressure, doesn't even need to have a mass per se. Anything at all, just through its existence, curves the fabric of space-time. And we're all living on a space-time, so we're all experiencing this curvature, and therefore we all have experiencing this gravitational effect and gravitational attraction if we're dealing with the Earth. We understand that the larger the masses, if we're dealing with masses, the larger the curvature is, and therefore the larger the gravitational attraction is. Now we understand that everything and everyone throughout the universe is connected through space-time and therefore is connected through gravity. And in fact, it's even deeper than that. We understand that there isn't such a thing as curvature at any single point. The very notion of curvature requires connecting different points with one another. In fact, for us here on Earth, this experience is quite tangible because we live on the surface of the Earth on a curved surface. It's not a space-time, but it's a curved surface of space nonetheless. At any given point, we may have the impression that the surface of the Earth is flat, and in fact, for thousands of years, humans believed that the Earth was flat. But it's only when you try to travel throughout the surface of the Earth and connecting different points in space together that this curvature of the surface of the Earth emerges. And so we're really trying to, on the surface of the Earth, follow a straight line. And straight lines, from the point of view of the curved surface of the Earth, I mean, looks like funny curves from the outside. But that's just a best way to follow as best a straight line as possible, adapting for the curvature of the reality we live in, adapting for the complexity of the situation in which we live. Now, you may have this impression that picturing gravity as a curvature of a fabric of space-time is just a cartoon picture that I drew for you or that Einstein drew for you, but in fact is much more complicated. But in fact, this understanding of gravity through the curvature of space-time is such a precise picture that it has enabled us to understand the motion of the moon around the Earth within a millimeter precision. We understand, for instance, how the Earth curves the structure of space-time around itself, and that affects the fabric of space-time where the moon is, and therefore affects the way the moon is flowing in space and time. And it even affects the way the moon is experiencing the flow of time. And once again, this is not just a cartoon picture. We understand this so well that if we wanted to predict the position of the moon around the Earth with a better precision, we will need to account for leaves growing on one side of the hemisphere in the spring while they fall down on the other side of the hemisphere in the autumn. And that changes ever so slightly the distribution of masses around the Earth, on Earth, and that changes ever so slightly the curvature in the neighborhood of the Earth, and that changes ever so slightly the motion of the moon around the Earth. We understand this picture of curvature of space-time so well that it doesn't even enables us to understand how we connect different points in space together. It also affects the way we connect different points in time together. And for instance, as we live our lives here on the surface of the Earth, satellites on orbit above our head feel a flow of time ever so slightly differently than ours because the curvature of space-time is ever so slightly different than what we're experiencing here on Earth. And that affects how we communicate with satellites, in particular with GPS satellites that are on orbit around our head. And so if we weren't adapting for the very subtle, small correction from the correction of general relativity in the fabric of space-time, the GPS positioning satellites and what they would tell us on our everyday devices and what it would enable us to communicate through Zoom, for instance, nowadays, will be completely useless. So nowadays, we are using Einstein's theory of general relativity in our everyday technologies much more than what you can ever anticipate. In fact, if we weren't using these very subtle corrections from our deep understanding of gravity, we would literally be unable to find our way here on Earth on a daily basis. So we really have gone a really long way in the past century in understanding the fundamental laws of nature. And I've been talking about gravity mainly, but really that's not only the only thing we have done in the past century. We're understanding the curvature of space-time. We're also understanding the structure of the sun. We're understanding the structure of the fundamental particles, the fundamental constituents of matter, the fundamental forces of nature, how this affects the universe from the smallest possible scales to the largest possible scales. So it's been a huge century of success, and we can possibly pat ourselves on the back. But at the core of all of this success, you may wonder as well if we haven't just unlocked Pandora box of challenges. Because the more we understand about how nature works and how it has been incredible at addressing some of the deepest challenges, the more we realize how little we understand and how much more there is to uncover. So at the core of all of this success is a multitude, a plethora of new challenging questions that challenges us on a human level, on a society level, but also challenges our fundamental understanding of the structure of reality. And this is really where you come in. This is really where we need the brightest minds to address some of the most challenging questions that humanity has ever been faced with. So I really want to encourage you to think about those things. My specialty, my expertise is in the area of cosmology, but in fact, we're using quantum field theory and the fundamental forces of nature with the understanding of space-time, with the understanding of the evolution of the universe to understand what the universe, how the universe was born, how it has evolved, what it's made out of, and where it's going. And one of the questions that we would like to address is that of its composition and how it is evolving. So to better understand this, let me take you on a small journey. And when I get to this small journey, I'd just like you to appreciate how already nowadays here on Earth, the level of understanding I mentioned we needed to have in the fundamental laws of gravity to be able to find a place here on Earth through GPS positioning devices, through understanding the very subtle correction that there is in the flow of space, in the flow of time, and the connection of space. Just imagine how deep our understanding of gravity and the fundamental laws of nature have to be to find our place in the universe and to understand the whole evolution of the universe. So let's go out in the universe. Let's go out of the solar system, and we're going to move out of our galaxy. We're even going to zoom out of our local cluster of galaxy. So you can see our galaxy here, and it's merged with different kind of other clusters of galaxies up to distances which are thousands of billions of kilometers. It would take us millions of years to get to those distances if we were traveling at the speed of light, which of course we can't. And on those distances, we already see that the clusters of galaxies, which you can see in colors in here, in bright colors, are embedded in filaments of dark matter, which you can see here in blue. Now, you see those in blue just because this is the best way to represent it. These are not real color. This is just an animation. It's just, in fact, a numerical animation. It's not just, it's a very, very sophisticated one, not by myself at all. But even though we cannot see dark matter with eyes, we cannot see dark matter with light, we can feel dark matter through its gravitational attraction. In fact, as I mentioned, since everything and everyone has an effect on gravity and is affected by gravity, anything that exists, even something which we cannot see with our own eyes, will have its imprint on the fabric of space-time. And so nowadays we have very strong indication that the universe is filled with dark matter, which are structured in filaments of dark matter, like you can see in this animation. And the galaxies, or the clusters of galaxies in which we live, are embedded in those filaments of dark matter. So even though this is an animation, it's in fact very good agreement with what we can actually observe through different kind of observational surveys. Now, on those distances, we already have strong indication that the universe is behaving in unanticipated ways. So for instance, we know that the further away we look, and the faster objects seem to be moving away from us. And that doesn't tell us that we live in a particular place in the universe. We have hundreds of years of Copernican principle to tell us that we really shouldn't think of ourselves as being privileged per se. Rather, what that tells us is that we're living in an expanding universe. The further away you look, the more space there is between you and those objects. And if the universe is expanding, space itself is being stretched. And so there's more stretching the further away you look, and the objects seem to be going away from you the further you look. The objects themselves are not moving per se, just like us in our galaxy. We don't have particularly the impression that we're moving away from everybody else. It is the space in between any two point in the universe which is being stretched. And we can understand that maybe the universe would have started with a big bang leading to an expansion of space-time, an expansion of space. But if there's one thing we know about gravity is that it is an attractive phenomenon. And so we would have expected that even though the universe is expanding, the gravitational attraction would have made this expansion slow down. It could even have come to a stop. It could even have been that the universe would have stopped expanding altogether to the point that it would have reached a point where it would start collapsing and return into a big, just a nothingness altogether, in the same way as it had started. But one thing in fact, we've discovered in the past 30 years is the expansion of the universe is not slowing down as we expected. As we look to larger and larger distances, the expansion of the universe is going faster and faster. The universe is expanding at an accelerated rate. And this is counter to what we would have expected if it were true that most of the energy present in the universe was according to this picture, where it's confined in the filaments of dark matter, which we can feel gravitationally, and the clusters of galaxies, which we can see. So to see if it's really true that most of the energy of the universe is in fact according to this picture, confined in the filaments of dark matter and clusters of galaxies, we can look at a region in the universe which seems to be completely denuded of any kind of matter, neither dark matter nor visible matter. In those regions of the universe, in between the filaments of dark matter and the clusters of galaxies, those are cosmic voids, which are millions of light years across. If we were to zoom into one of those cosmic voids in the middle of nowhere, just imagine how lonely you would be there. There would be nothing at all. There wouldn't be any galaxies, there wouldn't be any matter, there wouldn't be any black hole, there wouldn't be any dark matter at all. And you would be millions of years to the closest galaxies. And yet you wouldn't be completely alone. Even in the middle of the most deserted regions of the universe, those are filled with quantum vacuum fluctuation, which fills all of the pockets of the universe. In fact, the discovery of the Higgs tells us how the Higgs mechanism works and tells us that empty space is never truly empty of energy. At the very least, it's filled with a quantum sea of the Higgs itself that has an effect on other particles, because that's how it gives a mass to other particles. And because of this equivalence principle, on which Einstein's theory of general relativity is postulated, we would expect this quantum energy to have also an effect on gravity, and therefore to have an effect on the whole evolution of the universe. In fact, we know already since close to a century that if you take Einstein's theory of general relativity and you include to it the energy of the quantum fluctuation that fill every pocket of the universe, this leads to an accelerated expansion of the universe. This is the most uncontroversial thing that I will be saying today. This has been known for close to a century. In fact, Pauli himself knew that, who is one of the founders of quantum mechanics. So this is the good news. In fact, we do observe that the expansion of the universe is accelerated, and we do know that when we take Einstein's theory of general relativity with what we know should be present from all of the particles that we know exist and their quantum effect and the quantum vacuum fluctuations, it should lead to an accelerated expansion of the universe, just like we observe. The only reason you probably haven't heard of this so far, or not all of you, is because the predicted rate of acceleration of the universe due to the quantum vacuum fluctuations of the particles that we know exist is at least 28 of orders of magnitude too fast. So that would mean that the space between you and your screen, for instance, will be stretched so fast that the screen would seem to be going away from you at a speed which is faster than the speed of light, and you wouldn't be able to see or hear or do anything. So clearly, the structures in the universe wouldn't even have existed if that were the case. We wouldn't even be there to ask ourselves the question as how we got here in the first place. So the real question to my mind is not really why is the universe so dark. You typically phrase the question of why are we only made out of 5% or a little bit less of the energy budget of the universe? Dark matter may be made out of 20% of the energy budget of the universe, and dark energy leading to the accelerated expansion of the universe much more. The real question is why isn't the universe way darker? Why isn't the quantum vacuum energy that acts a little bit like dark energy, leading to the accelerated expansion of the universe, doesn't completely dominate the energy budget of the universe to the point that we shouldn't even exist? So we live in a very dark universe, but yet we are lucky that it's not way darker. And to understand why the universe is the way it is, people typically ignore the vacuum energy for yet unexplained reasons because it's such a deep and challenging question to explore that it challenges us at our core. And it's so embarrassing that people prefer not to address that question at all, ignore the vacuum contribution. And so if it is not there, then we need a new kind of energy to lead to the accelerated expansion of the universe. And so for that, people typically postulate the existence of a new kind of energy, yet unknown, which is unlike any other classical kind of energy that has ever been detected. And let's just call it dark energy, which is just a placeholder for our knowledge, is just expressing our lack of knowledge. But what I like to do in the last few minutes, and then I'll stop there probably, is to just explore the possibility that we don't need to ignore this quantum vacuum energy. After all, we would expect it to be there, and we would expect it to lead to an accelerated expansion of the universe. So we may as well just embrace it, but for that we need to understand why it doesn't lead to such a ridiculously large accelerated expansion of the universe. Now, Einstein's theory of general relativity, as I already mentioned, is built on the premises of this equivalence principle, on this universality. Universality is at the core of Einstein's theory of gravity. And that tells us that if we take two galaxies which are located on the other side of the observable universe from one another, this is 10,000 million trillion kilometers away from one another, we will still expect them to have a small gravitational attraction in each other, but that is really very small because it decays like the square of the distance, roughly like Newton's square law. So this is really extremely small. However, the universality premises on which Einstein's theory of general relativity is built tells us that to understand the evolution of the universe on those scales, we need to account for all of the energy present in between, and not only in one dimension, but it's actually a space-time. So we need to do that in all three-dimensional space plus the dimension of time. So since the very beginning of the universe, we need to include all of the contribution from the vacuum energy since the beginning of time itself. And it's really this huge level of vacuum energy, not just in between those two, but really throughout the whole three-dimensional universe, plus the whole time dimension since the beginning of time, that leads to an incredibly large accelerated expansion of the universe. But could it be that the underlying symmetry under which gravity is being built is not entirely perfect? In which case, it could be the case that only a small fraction of the vacuum energy contributes to the fabric of space-time, the curvature of space-time, and therefore to the evolution of the universe and the accelerated expansion of the universe. If it were possible that only a smaller fraction of this quantum vacuum energy would contribute, it would lead to a smaller accelerated expansion of the universe and therefore be potentially consistent with our observations and with the actual rate of expansion, accelerated expansion of the universe. So in Einstein's theory of general relativity, because of this universality, or what is also encoded in some of the symmetries of Gauss' law, already in Newton's square law, which is built on the same kind of premises, if you consider 2 points and you look at the force in between those two masses, the force decays like the square of the distance. So if you take the force and you multiply by the area, you get a constant in Einstein's theory of general relativity. This is what it tells you, that in Newton's square law, that the force decays like the square of the distance. That means that there's a conservation. If you take the force and you multiply by the surface of how far away you are from the source, you'll get a constant. This is related to Gauss's law, and this is related to some sort of conservation that is present. But if the symmetry that underpins Einstein's theory of general relativity was slightly broken, there could come a point where the force of gravity will sort of switch off. It wouldn't be completely constant anymore. It will come to a point where the effect of the quantum vacuum energy beyond some distance switches off. And therefore, it doesn't any longer contribute to the curvature of space-time beyond a given range. That would be the case if we're dealing with a finite range gravity, and this is where massive gravity comes in. The only possible implementation of a theory where the force has a finite range is in one way or another to postulate the fact that the particle that mediate that force is not a massless particle, as would be the case in Einstein's theory of relativity, or is the case in electromagnetism, but is actually a massive particle. Not in the sense that it's massive and huge, but in the sense that it itself acquires an inertial mass, and this inertial mass impinges in the dynamics of the force itself, in the dynamics of the mediation of the force itself through that particle, and means that it only can propagate for a finite distance, and therefore the range of the force that it can propagate is finite. In fact, the possibility that gravity itself could be of a finite range, and therefore that it corresponds in one way or another to a theory of massive gravity, is something very natural. And even though Newton himself came up with the Newton law of universal gravitation, he himself contemplated the possibility that gravity may not be as universal after all, and that could come a point where gravity would switch off. He contemplated that possibility. And in practice, what that would mean is that even in Newton's theory of universal gravitation, it wouldn't be universal, it would be a sort of massive equivalent of his force. And Laplace, after him, was a French mathematician, also contemplated the possibility that Newton's gravity could be of a finite range. And when it came to the beginning of the last century, or 100 years ago, when quantum mechanics came about and general relativity was already there, Pauli himself, who is one of the fathers of quantum mechanics, understood very well how to think of gravity as a quantum effective theory, where you could think of the particle mediating the gravitational force as a graviton, and those can lead to gravitational waves. He also very naturally considered the possibility that those particles were massive particles. And Salam, after him, who worked at the theory group at Imperial, not called the Salam Centre at the time, but now we call ourselves the Salam Centre, who's the founder of modern physics, I would say, the fundamental laws of nature in the way we're understanding of unification, but also understanding how we can implement some level of symmetry breaking within the standard model of particle physics. He himself contemplated the possibility that there could be a symmetry breaking for gravity itself, and that the universality for some of the aspects of gravity under which Einstein theory is built could be slightly broken. But throughout the centuries, even though those possibilities were being considered, it was always impossible to make it work fully. Not because it was inconsistent with observations. In fact, that's quite the opposite. Understanding how to implement a theory of a massive gravity could help with some of the most recent observations, but simply because it seemed to be impossible to make it work in practice. And that's until those two incredible gentlemen came along, Gregory Gabadadze, who's at NYU, and Idri Tolle, who is also at Imperial, also in the Salam Centre. So I don't want to go in the details of how this theory of massive gravity can work after all, but perhaps an analogy is to think of the theory of gravity, massive gravity, as all of the pathologies that people had thought would be present in such a theory, and thought about it for centuries. We found a way to confine them in a closed subspace of constraints where they can't escape from and they can do no harm. Mathematically, it's a little abstract to think of this, and we need to rely on some slightly more abstract dimensions. So that's why I thought this picture of the ancient stone is actually quite a good representation of what is happening. But perhaps more interestingly is to understand the consequences. And so to really understand the consequences of what it means to have a theory of massive gravity, we have to think of how we communicate with our universe. As I mentioned, we understand how we communicate with the universe through light most of the time. The light is the shaking of electric charges. When you have in a bulb, electric charges are being shaken and they produce light, which are electromagnetic waves. This is how antenna work. And this is also why you see, for instance, lightning in the sky when it's a very heavy charged day. And that corresponds to a quick acceleration of discharge of charges of electrons in the sky. Now, the same thing happens for gravity itself. And when we shake things around which are charged with respect to gravity, but I said anything is charged with respect to gravity because anything connects with gravity. So in fact, you can shake anything at all. So just imagine if you shake your hands like this, you would produce waves, but not light waves, not electromagnetic waves, but waves with respect to gravity, which we call gravitational waves. In fact, if you were imagining you were dancing with your partner, that would correspond to shaking around different masses, and that will lead to the production, to the radiation of gravitational waves. Now, perhaps sadly, those gravitational waves are very, very, very small intensity, and too small to ever being observable when I shake my hands or when you dance with a partner. But if you're considering masses which are strong enough in being pulled together and merging together at a very high rate, then those masses would distort the fabric of space-time around themselves so strongly that they would produce gravitational waves, which once emitted, travel through space-time for millions of years at the speed of light, deforming that space-time till they reach our instruments. They deform space in our instruments, and we can measure that deformation of space. And that's how we measured and we observed the first gravitational waves. This is on the left, you will see the first signal of gravitational waves observed in 2015 and announced in 2016. Of course, since then, there's been many, many, many different events have been observed. And so what it means is that in Einstein's theory of general relativity, all of those frequency, all of those colors of gravitational waves are completely universal and they travel exactly at the same speed. But if you have a theory of finite range gravity or massive gravity, because you change ever so slightly this equivalence principle, this universality of gravity, it means that different colors of gravitational waves would travel at a ever so slightly different speed, which is not visible within the range of what has been seen at LIGO, Virgo, Cagra, because this is relatively high frequency. But if you imagine much lower frequency gravitational waves, they could come a point where we start seeing that the gravitational waves, which are lower frequencies and are emitted first in the signal, travel ever so slightly slower than the gravitational waves at a higher frequency, which are emitted later in the waveform of the signal. And therefore, the signal that we would observe will be slightly compressed as compared to what would happen in Einstein's theory of relativity. So this is a very dramatic effect. We would never expect something to be quite as strong as that. It's just for visual purposes here. And as I mentioned, the current gravitational waves that have been observed, they are relatively high frequency for what gravitational waves are concerned. But in the future decade, we are hoping to have interferometers being launched outside the Earth in space, just following the Earth in its orbit around the Sun. This is an artistic representation of one of the instruments for LISA. And through those, we're hoping, us human, hoping to observe gravitational waves at a much lower frequency and possibly being able to distinguish between the speed of different gravitational waves, and therefore being able to diagnose a very small, subtle departure from this universality of gravity. So now what gravity will tell us in the future is for the next generation to tell us. These are the next generation on the blackboard, but I thought it'd be fitting to tell you a little bit what it means in practice to do the kind of research that we do. What do physicists do? So of course, there's a part of physics which is extremely important, which is related to the observations themselves. We need to look at the world around us and really understand what it tells us. Everything that we know comes from just listening to what the nature has to tell us. And so the fact that we think that there is such a thing as dark energy or an analog, an alternative to it that leads to the accelerated expansion of the universe, this is really the universe or nature telling us that. But once you hear and listen and observe and feel nature and the universe around you, a big part of that is to analyze the data that is at our disposal. And a huge part of what is being done in research nowadays, and will become bigger and bigger, this is all the recording of data at CERN, for instance. This is the biggest storage of data on the planet. And this is me next to some of those data storage. This data analysis and being able to separate the data that you want to keep and not and make sense of these data is one of the most overwhelming, but also one that's been the most progress done in the past 2 decades, and really where all of the machine learning technologies that we are using nowadays have originally come from. And then the third thing that happens in the physics that we do is once you have listened and heard and felt and analyzed the data, you want to come with modeling of what it tells us in terms of the description of the world around us. And that is the most theoretical part. This is where I live, in fact, where we do a lot of the theoretical modeling to understand how to come up with new models that can explain our observations and lead to new signatures that we can look with future surveys and observation. And that's what leads us to the current model, for instance, of the universe that we have today, which is in impeccable agreement with observation and experiment, but can always be refined. And I like to also say that this picture that you may have here of observations, or what it means to be a researcher, a physicist, a scientist, is in fact the complete opposite to some of the pictures that you see typically of Einstein just by himself on the blackboard, or someone just looking at through a telescope. Is actually quite the opposite of this. Being a researcher nowadays means being part of a huge international collaborative network. I have more than 130, probably more than 150 co-authors, which are in a lot of different places in the planet. I really very hope that by the end of my career, I could have collaborated with everyone on the planet, on the country, different country, everywhere in my planet. And it's really being part of a huge international endeavor that contributes to discoveries which are big and small, and not discoveries every day, but in fact, really the strength in doing the research is not the big flashy news that you may hear of. It's actually the little steps. These are the most important things that happen. And this is really where most of the work is, and where the little discoveries lead to something which is impactful and significant. And let me just say really that physics is everywhere. As a physicist, I really do believe that what we learn to do is to tackle some of the most fundamental and challenging questions of humanity, this fundamental question of nature and the universe themselves. We learn to model them, to address them, and articulate creative solutions for tomorrow. And so physics isn't just on my blackboard or in the lab, it's actually everywhere. And if you learn to tackle some of the most fundamental and challenging problems that nature ever had, then you can explore the solutions to that everywhere through society, in every field, and globally on the planet. And therefore, being a physicist is really what enables you to have all the doors open and make a significant and impactful difference for your future life globally on the planet. And I just want to end up here because I had these pictures of what it meant to be a physicist, but really this is what it means to be a physicist. These are all the women in physics at Imperial, and I'd just like to conclude here. Please join us as a friend of the Salam Centre, as it is a mission to use fundamental science as a unifying tool in many different ways. So thank you.
Thank you very much, Professor, for your wonderful overview about your work and about your experience. And I must admit that I have so many questions to ask you. However, respecting the time boundaries of the session, I'd like to move from uh, theories we learned right now from them towards the experience that brought you to this frontier. So, in a recent interview that I was watching of yours, you had mentioned that you are handling this frontier career, being a mother of three. And I would like to ask, how do you balance such a world-class research career with family life, and what advice would you give young women who are considering a career in physics?
Yeah, so it's an excellent question, and let me just say up front, it's not going to be easy every day. And so if you do find it challenging, and if you have questions, and if there are times where you feel like there's too much and it's really overwhelming, I'm not saying that's good, but I'm not. It's not. It doesn't mean by any stretch of imagination that you're not doing the right thing. Sometimes it is overwhelming, but you have just to keep through it. We have gone a long way in including a much more inclusive and diverse level of research, but I think we still have a long way to go to make it much more real, because it's not easy. It's not easy every day. I think you need to focus on what you can actually do that makes sense. There's so many different things that you can do, and I would say as a woman in physics, it's very easy to be overwhelmed with lots of different requests because people want you for lots of different things. And so one thing that I've learned, not very well, but I would really encourage, and I tell all my students and postdocs to do that. I don't do that very well myself, but I would encourage everybody else to do that, is learn to say no so that you can really focus on what is important to you and important to your family life. I think you need to be able to realize that your family life or your private life is something that is really important, and without which you wouldn't be able to do the kind of research and the kind of impact that you have. It's not that I juggle my family life with my research. It's that in order for me to be able to have a creative level of research, my family life is very important. It is part of who I am. I would be a very different person without my three children. They really challenge me in many different ways, and they ensure that I keep some level of creativity. Sometimes I see them being so creative, so inquisitive in the questions that they ask, that I realize this is why we're doing it. It is for them, but it's also because us as human, we have this thirst of knowledge. So I think it's not that I juggle things, it's part of a bigger ecosystem where we work in it together, and they help me in much more ways than they can imagine.
That's such a nice perspective, Professor. One more question that I would like to ask you is, you were providing advice to young generation about how the young generation needs to explore more questions about physics, theoretical physics, or even conceptual physics. Uh, I would like to be more specific, and I would like to ask you about what more of an advice would you give to young students who want to pursue a career in theoretical physics today, and what do you think is the most exciting unanswered question in cosmology, or even in astrophysics, or even in the general sense of broad physics right now?
Yeah, so that's a difficult question because things are very much in flux. I would say what's really exciting, since we talk about cosmology and related to astrophysics right now, is a wealth of new data that we have, but also while it's becoming more and more precise, we're actually having signs that things are maybe not quite as trivial as what we would have expected in the first place. So this to me is very exciting. I think what is important is to keep some of this curiosity alive. I think as you go on, there are sometimes the, you may sometimes be going to direction where you're complacent in the kind of research that you do or in the kind of assumption that you allowed for yourself. And so after a while, you have everything set up as granted, and you just focus on the same direction, forgetting that you started in the field, you started that because you were excited by the questions and the depth of the question that you were allowing to ask yourself. So what I would like to ask you is keep it alive, keep challenging yourself. At the beginning, it's quite hard because there's so many challenges that you just do the best that you can. But after a while, I see there's a transition where people then just focus on the expertise. And of course, you need to have your expertise, but stop asking themselves the very provocative kind of questions that they were asking themselves when they started the field. And that in itself is not necessarily, it's good to some extent, but you need to challenge yourself and try all the time to think about how you can go beyond your comfort zone. You start addressing some of those questions because you're enjoying some of that level of challenging yourself. And it's good to keep some of that level alive throughout your career. I think it will come a point very naturally where we will be able to do more and more with machine learning, with AI, and some of the very challenging ways to carry out calculations and bring things across will be done by machine learning. And so I think it will make the value of the questions much more interesting. It's not about being able to answer a question, it's about being able to understand what are the relevant questions to ask ourselves. In fact, in my research, most of the time we spend months to really being able to come to the point where we can finally articulate the right question we're asking ourselves. And once you understand, this is in fact what I like to understand, this is how I should phrase my question, then it's much easier. Once you know how to ask yourself the question and what it is precisely what you want to ask yourself, then you can follow things through. And then that's why just focusing in the same direction and not asking yourself more and more questions, this is when you stop really doing the exciting and challenging part of research that we're supposed to be doing.
Thank you very much for your precise analysis, Professor. Building up on your answer, I'd like to explore about the graduate school situation, where graduate schools are full of dead ends that don't make it into the final papers. Can you walk us through one specific calculation or approach that you abandoned and how you knew it was time to abandon it rather than push through and work on a different set of paper for your graduation?
Yeah, so that has happened a lot, that you start exploring a question and maybe things are not following through exactly the way you want, or maybe they even do, but then the answer is not that exciting after all, or the effect you were looking for are not that important after all. And I think this is really one thing I want to say is what I mentioned before. What is important is not really the big flashy big discoveries and big paper that you can flash out. It's the little steps. Even if you feel like a project itself didn't really lead to the completion you wanted to have, you grow so much from those projects to the point that it's often hard to remember. But every single connection, every single failure that you went through in those projects has actually had an impact in you and will have an impact on other projects later. So I can give you some examples of papers where I was exploring, I had something in mind and I was thinking of how, for instance, I had a model of gravity where I was thinking maybe working with extra dimensions, we could weaken the behavior of gravity on short distances. Typically, you'd think that if you have a theory of gravity and you look at things on shorter distances, then you need to include more and more things, and therefore gravity is only going to become more and more attractive. And I was thinking, well, maybe if we can rely on things in extra dimensions, we can make it so that the gravity would become weaker and weaker at short distances. At the time, I was thinking of this for many different reasons, in parts in addressing some of the cosmological constant problem, but also because there had been for a little while, some years ago, some hints, and then they went away, but some hints that gravity could be ever so slightly weaker on shorter distances, but that wasn't the case. Anyways, I was coming up with a model where I thought, oh, maybe we can do that. And then I worked for months on it, and then I realized, well, it's actually not, it doesn't quite work. So it had to be aborted really. And so what's the most important is just to, for yourself, first of all, understand what are the lessons that you have learned from that. And once you take it from that perspective, as opposed to this is what I want to present to the world, but more this is what I have learned from that, then it's much easier to then summarize those results and put them out as a paper in that sense. But from these lessons for myself and from a much deeper understanding of what was possible and what was not possible and why it wasn't possible, then I was able to follow up with another paper, another project, which was in fact very much exciting, where I could actually see things working out in quite a different way. And that would not have been possible if I hadn't gone through these many failures along the way. So failures in science, failure in research is a good thing. You may have the impression that it's an embarrassment and that you should just abort the project and then just give up. But actually, we would never make any progress if we hadn't gone through all of those stages. And you should really remember that you're doing that for yourself. You're doing that because you're excited and because you have learned from those things. And so this is what should come across at the end of the day.
Also, Professor, while we see many high school students or even undergraduate students very interested and keen to pursue theoretical physics or a career in science or generalist STEM technology, but they are probably restricted by thinking that my household does not belong to science, or I do not come from a
Yes.
science background, or
Yeah.
maybe I do not come from a very resourceful background.
Yeah.
Uh,
Yeah. Yeah.
I would like to ask about how your upbringing was, and did you come from a science or physics background, and how did you make it to the top of the line for a woman in STEM? And I would like you to provide a sort in encouragement speech.
Yeah.
It's for students who are actually actively
Yeah.
trying to pursue a career
So
in physics.
absolutely, and really go for it. I can tell you many different things. The first thing I can tell you is that um, particularly theoretical physics requires no resources. It's just everything is in your head. It's at the point where you barely need even a pen and paper. You can draw things in the sand, but it's really about the thought process. So I really think that theoretical physics should be accessible to everybody. Everybody can think about things. There's no limit to imagination. There's no limit to how you can think of things. No one can prevent you to think about things, and therefore everybody belongs in theoretical physics. I don't understand why not everybody is a theoretical physicist. In fact, I do think everybody is a theoretical physicist. And often people ask me, well, why where did that come from? Why are you curious about things? Why did you decide to do physics? And for me, this is a strange question because I don't think I ever started to think that, oh, I want to become a theoretical physicist. I think it's quite the opposite. I think we all are theoretical physicists. We're all driven by those curious questions. And I can see those in kids everywhere. And I've grown in many different countries. I've grown in many different places on the planet. And I can tell you there's a universality that every kid on the planet is curious. This is something really true. It doesn't matter what your background is. It doesn't matter what your upbringing is. It doesn't matter what the culture is. Every kid, every kid on the planet likes to drop things. They drop things everywhere, wherever you are. Even if you're in the middle of a civil war, kids will experiment with the environment, experiment with the laws of nature, because this is how we are as human. This is something very universal. And so we like to challenge things around us, and we like to use that as an opportunity to understand things around us. And I think what happens is for some people that stops at some point and they stop becoming theoretical physicists. So just don't let it stop. Don't let it stop. Just continue being who you are. Continue being a human as we all are, and ask yourself questions and challenging yourself. Just continue. Just don't stop. That's the only thing. Now, it requires no resources at all, so anyone can do it. But maybe more pragmatically, is I can say these inspirational speeches and I can tell you can do it, everybody can do it, but there's so many times where it becomes so challenging. And maybe I give the impression that I have overcome all of those challenges and I feel like I belong there. But every day I feel is so daunting. Everybody has this kind of imposter syndrome that they don't belong there. And people express that in different ways. Some people express that in a protection mechanism where they give the impression that they are above it and they belong to it so much that they are themselves what it means to be a theoretical physicist. Whereas other people feel like if they feel like that, they must be alone and therefore they must mean that they don't belong to this environment. And that's really wrong. I can tell you every day is a challenge and every day I wonder, do I really belong? Because no one looks like me. No one comes from the same background as me. No one thinks exactly in the same way as I do. And therefore, maybe it means that I don't belong here. But in fact, it's quite the opposite. If we all thought in the same way, if we all came from the same background, then we wouldn't have different perspective and we wouldn't be able to move the field along in many different creative directions. It would be really boring. It is this diversity in approaches, in upbringing, in the way we think of things, in the different ways we make connections in our brains to think about a problem that makes all of us so valuable to doing theoretical physics. If we were all the same, then it would be stuck. Then there would be nothing to do because everybody would think exactly the same. And that's it. Then you wouldn't bring anything to the field. It is really your uniqueness that brings what is the most valuable to the field. So it's really important. It's not a feeling that I would say goes away for me. It's not a feeling that I appreciate. It's really challenging. But it is very much the fact that you don't belong there, which means that this is precisely why you belong there more than anyone else.
I completely agree with you, Professor. Even while researching and reading about your articles, your biography, I found out that even you were enrolled in an engineering degree at first at École Polytechnique, and then moved towards a master's at EPFL and to a PhD at Cambridge DAMPT, Department of Applied Mathematics and Theoretical Physics. And I would also like to tell our audience, on top of what Professor said, to pursue their passions completely, be honest to themselves, and never give up on what they are doing.
That's right. That's right. That's right. Absolutely. It's really very important. Yeah.
Yes. And Professor, talking about our mission, the mission of ScholarPath and Abdus Salam Centre, ScholarPath and Abdus Salam Centre are approaching the same problem, access to frontier science for low resource background peoples. From two different starting points, one a grassroots student founded effort in Nepal, and the other established in a premier institute in London. Um, what do you see as the actual mechanism by which a partnership between something like ScholarPath and the Salam Center could move a student from inspired by a podcast that we are holding right now to doing publishable quality work and pursuing their dreams and making them into a reality?
Yeah, so I think the good thing about theoretical physics is, as I mentioned, you requires very little resources. So I think it's a lot about being able to collaborate and exchange ideas. So a very natural, what you're doing is the first step, I think, where we discuss, we share interest, and we have questions, and we can address this. I think is the first step. The second step, I think, is also to engaging as you do in ScholarPath, and I think the Salam Centre is very much doing that as well, engaging throughout society, particularly in pockets of the society, wherever it is, that feel they may not belong there, and then realizing that this seed for curiosity and this potential to contribute is being present. I think this is important to make sure that everybody feels like they can contribute, and there are kids that may come from very underprivileged backgrounds and they're not even realizing that it is in themselves to actually addressing those questions. And then I think having access to the exchange of ideas and to how people think about different projects is very important. And nowadays, luckily, this is becoming more and more accessible. You have access to all sorts of resources. There is the archive, which gives that free access to anyone throughout the planet with no required to have any membership or anything, to all the papers that come out every day. So I think it's really important wherever you are to go through this archive and understand, set up little reading groups and understanding what makes sense, what makes less sense, and how to move forward in those directions. Nowadays, there's also so many talks online, which is really, really important to just going through what people are thinking about at the moment and moving forwards in those directions. Then with the Salam Centre, what we have is more fellows. Some of them come for collaborative visits. Some of them are part of some engagement programs. Some of them we will want to make sure that we can help each other in coming for the master program. I think the education side and making sure that there is access to some level of education for everybody will be very impactful. We very much hope that in the future we can come up with more and more scholarships to encourage people to apply for those scholarships, and once they have them, then they can come whatever institute they want to do a degree, a focused degree in theoretical physics. And I think that is the first step towards then being exposed to all of the novel ideas and have their own creative and impactful research themselves. And as you say, being able to publish their work on journals and on the archive themselves.
That is such a precise analysis, Professor. And we would like to build up on what Professor said and let our audience know that ScholarPath exists just for this mission of providing scholarships, providing resources, and even premium papers to some students that we deem that the faculty of Imperial College London or the Abdus Salam Centre of Theoretical Physics deems as qualified, and allowing them access to some of the premium resources of the Salam Centre as well through our collaboration. And the main goal of ScholarPath is to provide resources that will encourage students to push through towards their dream and towards their future. And alongside that, Professor, I'd like to ask one more question about your lived experience, and then hand the stage to my fellow members so that they can also share a piece of their mind with you. Um, the question is, working alongside a partner who is also your scientific collaborator is very unusual these days. What's one thing about that dynamic about you and your husband that's genuinely made the physics better, and one thing about it that's genuinely made it harder?
Yes. So in fact, it started much harder. I would say it wasn't obvious in the first place. And the first few years, I would say the first 2 or 3 years, we made a rule that would never talk about research together, because it was really challenging and it does affect the dynamics quite significantly. I think for us, and every relation is different, and I'm not saying this is the way to go for everybody, but I can share you my experience, our experience. For us, it was important to start with a clean slate, and where we were building our relationship together to the point that there was really such a deep trust, such a deep understanding, such a deep, really being able to intuitively follow the thought process of the other person, as you do in any other kind of relationship. And it's only once this was really there, so grounded in our relationship, that we couldn't prevent ourselves then sharing our excitement about the research itself. And so nowadays, for me, when I'm excited about something, of course you want to share it. And if your partner understands it, then it's very easy to then follow up and something which will end up being a collaboration. And it's a very natural collaboration, which is maybe not so smooth every day, but most of the time it's smooth because you don't have any filter, you don't have any way, you don't need to protect yourself in any way or pretend one thing on another. and you understand each other so well that much fewer words are necessary, and somehow you go much deeper, much faster, and it's much more efficient than in many other collaborations where there's so many different layered levels of communication and guarded discussions that you have to constantly permutate between them to actually go to the message. You say something, but you mean something else, and you had him on something else, and you protect yourself in many different ways. Whereas when you're in such an intense relationship, it's actually much more fluid, much more permeable. So nowadays, often we don't even need so many words. Sometimes my partner just writes something and understand exactly where he's coming from and what he means. And then he also understands exactly what I can bring in and how we're going to make progress together. And I think this is really a very, very strong strength. Um, it drives our kids a little crazy sometimes, but they got to grow with it as well. And it's funny because I can see that in their way of thinking about the world, even though they are young, they don't do theoretical physics per se, but still it's about how they analyze things around them. And you can see as well, I can see from there exactly how they address a problem. And it's different for each one of them, but it is there and it's something you learn to know so much about the other person that you know how to work with them in a much more efficient way.
That
But it's
was
like families. Yeah, there's families are intense in so many ways. So the intensity is definitely there. It never goes away.
that was such a wonderful overview, Professor. Thank you very much for that.
Thank
And
you.
now I would like to hand over the stage to my fellow colleagues if they have any questions to ask Professor.
So hello.
Hi, Ivan.
So you know what? I came here with a long list of questions, but you have already answered every single of them with iron. So
Ah,
now I have so I so now I need to come up with the new ones. Yeah. Just from curiosity, I just want to ask you, why did you pick Imperial College London?
so I only been here 10 years per se. It's a long time. It feels like a long time, but also it doesn't feel like such a long time. So I was in other places before. I think what appealed me to being here is really the stimulation, the intellectual stimulation. And I'm
Mhm.
not I'm not bored from that respect. It would have been easier to stay in a smaller place and probably I would have been quite happy in my future career staying in perhaps a smaller place or a different place. But it did challenge me to come to Imperial. It wasn't easy. It's in the center of London, which is an amazing place, but also it makes everyday life much harder because you are in a big city, it's busy, it's really expensive. But that comes along with all of the intellectual stimulation that there is. I think what's really incredible for me is because we are in the center of London, there's so many people coming through, and there's so many other institutions around in London, in the UK, in Europe. It's very easy to go to Europe and collaborate with people there. And so it really creates a hub of opportunities, not only in research, but also in how we connect with society. We are in the core of many of the very big media engagement opportunities. And so for me, that's very exciting to be part of that as well. But also where we are in the UK, it's a it's a on the one hand, it's a very privileged part of the world, but it's also very close to some very, very underprivileged part of the world. And so being able to discuss with the people there and ensuring that science is accessible to all is very, very important to me as well.
That sounds amazing. I want to have this feeling for once.
So where are you?
I'm in Germany right now.
In Germany, I see. I see.
Yeah. Okay, thank you.
Thank you. Thank you, Evan.
So I was restraining myself from asking any physics-related questions to Professor in this podcast, but it seems like I cannot restrain myself any further. So I'd like to ask you about your work. The DRGT construction is specifically engineered so the ball-wear-disser boost cancels at every order in the non-linear expansion. In your work, what was the key structural insight that told you and your collaborators the tuning would survive beyond the leading order before the full nonlinear proof was completed?
Yeah, so that's an excellent question. The reality is, when I started working on this, in fact, I was convinced that it wouldn't work out because there was all of those no-go theorems that were showing that it shouldn't work out. So instead, I was basing myself on extra dimensions and understanding the structure of what gravity can tell us. So nature itself tells us how it wants to represent itself, also in higher dimensions. And so being able to understand what you can learn from its structure in higher dimension and what are the relevant building blocks in there, that's really what gave us the intuition of how to make sense of it from a four-dimensional point of view, and how you can think of some of the features that may arise in higher dimensions actually can be represented from a four-dimensional point of view as a correction and a mass term. But because it comes from higher dimensions, gravity, general relativity, it had to evade the Ballward as a ghost in this case because it is just gravity, albeit with more degrees of freedom, but just gravity. So there would have been a way to make it work in higher dimensions. And so understanding how that works out and how that evades the Ballward as a ghost, even non-linearly in higher dimensions, this was very much the insight that made it possible to understand how we can translate that back into a four-dimensional local perspective and get something that would also evade the Ballward as a ghost from a standard picture. But let me just say that, in fact, what did the trick is realizing that the way this constraint exists in higher dimension is not as trivial as what people thought it was, and it requires some mixing between the different degrees of freedom. And it's understanding what is the underlying structure and the mixing that makes it possible for this to be realized in higher dimension that helped us very much understanding how we had to rethink of it from a four-dimensional point of view.
That's wonderful, Professor. I would really love to collaborate, be the first collaborator from Nepal on your research works and later in the future. And I'd like to once again ask my colleagues if they have any more questions to ask Professor about her work or maybe about her experience or anything.
Hi everyone. I had a question. Hi Professor, it's a pleasure to talk to you. Am I audible?
Yeah, I can hear you. Yeah, hi.
Yeah, okay. Hi. So, what do you think that even today are the biggest barriers that women still face in theoretical physics? Is it maybe hiring, funding, promotion, or entirely something else?
Can you say the first part of the question? What do you want to know more precisely about women in theoretical physics or more generally
Hi.
theoretical physics?
What are the barriers that women face in theoretical physics today?
Yeah, so the barriers are incremental in the level of challenges throughout the career. I think there's not a single thing which makes it harder necessarily per se for a woman or not, but the obstacles are there at every single way, every single level along the way. And sometimes for me, I can tell you for me, and I think the experience is very different for everybody, but for me, it's the accumulative side of things. When there's one challenge, you can just say, and I hear my daughter say that, and I really like it, and I can hear her say, "Well, I'm just going to show them I can do it." And when I started the field, I was like this and say, "Well, people think I can't do it, so let me use this as an opportunity to show people I can do it." And I would go it, and I would show, and of course everybody can do it, so you can push yourself But there comes a point where maybe you become quite tired to keep needing to push yourself. And that point comes at different levels for different people. And I think one of the big challenges that I can see that with my female PhD students or for my female postdocs, they come a point where they are tired to feel like they constantly need to justify themselves. And that comes to me as well. Sometimes you feel, okay, enough now. I should just be able to do what I do without all of the constant obstacles that come along the way. It's not that you can't address and go beyond every single one of those obstacles. It's just after a while, it's really tiring, and you wonder whether your strength is not better appreciated somewhere else. So I think that comes along. There is some level of fundings to encourage women, particularly at earlier levels of their careers, which I think is really good, to encourage women more women to go into the field. I think this is really good, and it's really important. I think at some point we need more critical mass. It's going to be important that if you're only ever the only woman in your field, then it always feels like a very lonely place, and it's very hard to understand how you can navigate this whole field. But if we reach a critical mass where in fact the dynamics has changed and it feels much more natural, then all of a sudden we don't need to ask ourselves all of those questions. But it is difficult, and I have to admit that we are, of course, a long way as compared to what it was 50 years ago, but there's still a long way to go. And I don't know if what is required is more financial resources, or if there's a completely different way to think about things. If I knew, honestly, I probably would have been better at trying to implement some of that. It is difficult. It is difficult. But I think doing exactly what people here are doing, it is this networking which is so important, and feeling part of something you can discuss with people and you can belong. I think this is the most important thing that is happening. And so I think ScholarPath is really, really doing an incredible service to the future society and the future generation by providing that platform where people can discuss and can feel like they belong to that, and they can move forward. This is really very important. And maybe this will stop later in your career, but having had that support to start with is really, really, really important.
Thank you very much for your very kind words, Professor. I have one more question from my colleague, Duongpa, who unfortunately cannot use their mic due to some situation. So the question they want to ask you is, working in gravitational wave astrophysics uses a lot of data from the internet to run simulations and analyze the data. And hypothetically speaking, some non-privileged student, someone who can't even afford a good laptop, how can they contribute to gravitational wave astrophysics in this scenario?
Yeah, so you don't need to contribute necessarily to the analysis of the data themselves. There's many different ways to contribute. The kind of research that I do, I don't even need a laptop, in fact. I just have my Blackboard, but you don't need even your Blackboard. The good thing is a lot of the science nowadays is open access. And so it doesn't mean that just the data themselves is freely accessible and available, but also the analysis and the results of the analysis, they are being published and they are there, and you can use them, and you can use them to ask yourself the relevant questions. I think this is going back to exactly what I was saying, that the trick is to understand what is the right question to ask yourself. And the beauty is there's no restriction in the kind of question you can ask yourself. And you may ask yourself some questions which require more resources, and then it will be more challenging to answer. I think this will evolve and it will be more openly accessible. But you can ask yourself as well other questions which are equally, if not more fundamental and important. And some of those questions, they require nothing other than your creativity and technical skills, mathematical skills, and understanding and intuition in the field to address.
Thank you very much, Professor. Thank you once again. And I'd also like to ask our colleague Anju, who joined a little later due to some of her works, if she has any questions to ask Professor or specifically wants to know about anything.
All clear.
Okay, so it appears like we have one more question from our collaborator, Yudong. Okay, they want to know that they have been thinking about this recently, but can we possibly detect dark matter using interferometers? If yes, how much and what information that we can know about dark matter?
Yeah, so this is an excellent question. You should think of gravitational waves as another messenger traveling through space-time. And so particularly if gravitational waves interact with dark matter, if they're non-trivial scenarios of dark matter, that will affect the propagation of gravitational waves. And this may be one way you can get more insight on dark matter. But also just by the presence of dark matter that affects the clustering, it affects the lensing of gravitational waves. And so in the future, we will be using gravitational waves to better understand their lensing and to better understand the distortion relations. And that will give us, it's like doing tomography, it actually gives us some insight on what gravitational waves went through between where they were emitted to where we are coming through. And the beauty with gravitational waves is that they are made out of gravity, they're made of space-time, distortion, and so they are affected by everything. They are sort of, they are not transparent to anything per se, like light that can travel through dark matter, if you will. So of course, the effect is extremely, extremely small. And to have a bigger effect, you probably would be in models where you have some non-trivial non-minimal coupling between dark matter and gravity. But in principle, something is there at every level.
Thank you very much for the analysis, Professor. With this, respecting the time boundary once again, I think it is time for us to conclude our podcast. Yes, sorry. Yes, Anju, you can ask through the chat. Professor will be glad to answer your question. Okay. Our colleague Anju here wants to ask that how can a computer or a software tell the difference between a dark matter particle and a regular solar neutrino hitting your detector?
Say it again. Can a computer tell the difference between a dark matter particle and a regular solar neutron heating your detector? The computer itself won't. The computer is just there for the analysis. So we have very good modeling on solar neutrinos. The rate of interaction is very small, and it comes in with a particular energy distribution. Now, for dark matter, we would expect them to lead to slightly different kind of interactions. And so it depends a little bit if you're doing direct detection or if you're doing the neutrino or the dark matter particle interact with one of your medium, for instance, in the water or anything like that, and then either lead to the decay into something else or what it leads to. But the signatures are different, and the energy scale is the behavior as a function of energy and how it scales with the volume and how it scales with the kind of medium that you're probing it with is going to be different.
Thank you for your answer, Professor. I think we should transition from the podcast session to discussing about the future collaboration for ScholarPath and the Abdus Salam Centre. Um, I would like to first thank you, Professor, for your extraordinary time and
Thank you.
giving us your extraordinary time and then letting us host you through this podcast session and guiding our audience, our students, our users through what a career in theoretical physics looks like, how a person that made it to the top of the theoretical physics line has their perspective on the career and how they can shape their career with little to no access to resources or even if they have resources. Thank you very much for that, Professor.
Yeah, and thank you, ScholarPath. It's thank you for all the initiatives and everything you're doing. It's really, really impactful, I think, for the field. Thank you.
Thank you very much.